Okay. So, hi everyone. This is, I don't remember exactly what lecture. Do you remember? No? Anyway, this is theory. Today, we'll talk about chapter 7. We'll talk about measure preserving dynamical systems that mix in some sense. So let's start with some ideas just to begin why we are interested in study mixing. So suppose you have a dynamical system, measure preserving dynamical system. I mean, by measure preserved dynamical system, I mean a measure space was a measurable map that preserves the measure me. Okay. And from this, we want to study how the system forgets the past as it is iterated. Okay, so suppose we pick a point. Okay. And we want to study how the system mixes in the following sense. When you have a measure preserved dynamical systems, the map F determines a deterministic system in the sense that when you have a point, if you pick a point X, you are able to determine all of its orbits. Okay, but here we're interested in study the relationship between when I have, for example, two sets, and I want to study how this set relates to this set. Okay. So for this, we start with some definition. We say the measure preserving dynamical system is mixing if for every A, B, this limit exists is equal to the product of. Okay, so this is the definition of mixing in this sense. So, as I was saying, this is somehow related to if you have a dynamical system, okay, you want to see how two different measurable sets relates in the future, as long as the system gets iterated. So when this goes to 0, this means that in the future these events in a probabilistic sense is somehow these two events in the probabilistic sense in the future are independent. Okay, so this is what mixing says in this sense. And this is the definition of mixing, and so we can see that this definition is for measurable sets, but we can extend the definition for any measurable function. So remark if psi are measurable, the correlation we define the correlation function as this. You take this correlation function, if you take the function phi, for example, as the characteristic function of a set A, and psi as the characteristic function of a set B, then it coincides with this definition right here. So indeed, we have the following equivalences. Let me state this as a proposition. Deixa eu parar. Talvez this. Let's see. Dynamical system. Done. The following are equivalent. One. Here I will do a simple notation. Here the notation for which I'm using is F me is mixed. I say that the system is mixing if the pair F me is mixing if it's mixed. It's just tautological. So the following are equivalent. F me is mixing. 2. For any phi psi L2, we have that the correlation function goes to 0 and infinity. 3 for any phi in L2. This any phi, the correlation function with respect to phi. Yes, let me see here. Yes. goes to 0. And 4. Here I will denote this. If you have an algebra, an algebra of subsets of this measurable space, such that the sigma algebra generated by A coincides with B, then this okay. So let's prove this proposition. Here, just to recall what an algebra is, for me, an algebra is a remark. An algebra is everything that you know about sigma algebra, but the exception is that instead of you consider arbitrary unions, here you consider finite unions of sets. Okay, this is the only difference. And when I say that the sigma algebra of subs of this algebra generates the sigma algebra B, what I say is that the smallest sigma algebra that contains A coincides with B. It's just things from measure theory. And is a sigma algebra. Let me. But with finite unions instead of arbitrary. Okay? And I will need a result from measure theory to prove what I want here. I think everyone has seen this kind of result once in a lifetime. But actually, this result is related to the fact that when I have an algebra of subsets that generates the sigma algebra, then the elements of B may be approximated by elements from the algebra. Okay? So recall the following results. Theory. This is the lemma. Phase an algebra such that the sigma algebra generated by is B. Then for every epsilon and every element of V, there exists an A such that the measure is smaller than epsilon. Okay. This is maybe you have seen this from measure theory as well. Is that the symmetric difference? One way I like to interpret this, to see this result, is that the measure me induces a distance on the space of measurable function or measurable subsets. And what I'm saying is that the algebra that generates my sigma algebra is dense in this metric space. Okay, this is what this lemma is basically saying. So let's prove these equivalences. I think the first one, maybe one implies, let me see the equivalence which we could prove. 2 imply 3 is obvious. Okay, so let's. So 2 imply 3 is obvious. And the work we have to do is basically prove that 2 and 3 are equivalent, 1 and 4 are equivalent, and then 1 and 2 are equivalent. Okay, so this is basically will be the proof. But let's start proving that 2. Let's start proving that 2 is equivalent to 3. So, okay, 2 implies 3 is obvious, so we have to prove that 3 implies 2. And how we do this? So, we're going to do the following. Let phi, we fix a L2 function, and we'll consider the following closed subspace, which I will denote by h phi. This is the subspace. This is the smallest closed subspace, such that the correlation functions are converging. Sorry, this is not the subspace I want. What I mean is that this space here will be the smallest closed subspace of L2 that contains phi and the constant functions. Smaller closed. I n. And they also satisfy this property, that when this space here is invariant. Okay. Here, UF is the Koopman operator, okay? That is. It's just okay. I will take this space, satisfy this property, and I will take this space here. That. which is the subspace we are interested. So the idea is to prove that this subspace here will be all L2, and this will get the second line. Okay, so now we start with the following remark. Is that this space is a closed subspace of L2. And this is just by definition. If you take a sequence of functions here, then any function converging L2 has to be here as well. And this space, by hypothesis, contains phi, because we're assuming 2. Sorry, we're assuming 3. Yes, you're assuming 3. And contains the constant functions. Okay, it's just plug the definition, you'll see that the constant functions are contained in this space. Now, as I'm assuming that my variant is also invariant, my measure is invariant, so we have that this space is invariant by the Koopman operator. Okay, because if you take a function here and you plug the definition of Koopman operator, and you plug the definition of this space, you have the sequence of correlation functions also converge to 0, because I'm assuming that the measure is invariant, so you have this property. And then you prove what you want. So this implies that the space that we considered earlier is contained here, because this is the smallest closed subspace that contains phi, the constant functions, and is invariant by my Koopman operator. So this space is contained here. And okay, so what I want to do now, I want to prove that the simple claim is that if I take the orthogonal subspace to my space H phi, then this is also contained in this space. Okay, but this claim is actually easy to prove, because if psi is here, then when I take the Koopman operator, if I take as my function phi is here, and the Koopman operator leaves this subspace invariant, then this function here is contained in H phi. So this has to be 0, because psi is orthogonal to this space for every n. N is 0. And we I can also check that the integral of psi is just in L2 norm this, but this function here, the constant function 1, is contained in the my space H phi that I built. And so this is also 0. And when I take the correlation functions, so when I plug the definition, what's this? What's this? This fine. L2 is this. The me. Okay, and psi. This is 0. Okay, but this is actually okay, because this is 0 for every n. Zero. So this proves that psi is in this space here. And this proves the claim and also proves that 2 is equivalent to 3. Okay? Sorry, there is no square yet. This is just that 2 is equivalent to 3. So now we are going to prove that 1 is equivalent to 4. Well, the first, 1 implies 4 is obvious, so we have to take care of the case 4 implies 1. So for this case, we're going to use this lemma here. So what we want to do, we want to prove that if A, B are arbitrary, then we want to prove that prove that so what we're going to do, we take epsilon, and for each one of each A and B, let A0 in the algebra, A0 and B0 in the algebra, such that the symmetric difference is smaller than smaller than epsilon for each one of these sets. Okay. From the lemma. So to get in this limit, we have to compare this limit here from what we know. We know that as A0 and B0 are contained in the algebra, then we have this limit here. So we know that Okay, this is just my hypothesis. I don't want to erase this. Can I erase it here? Okay. Now I want to get this estimate, but before, if you do this, if you take the symmetric difference between these two, this will be contained in the metric difference union B metric difference 0. This is just a general property. Okay, if you want, you can convince yourself. Just open the definitions, and it's not that hard. But it's a general property of the symmetric difference. And okay, this is first remark. And another one is that the difference this difference is less or equal than the difference of the symmetric difference. Okay, this is also a general property. So from, I should, maybe it's better. This is 1 and this is 2. So from 2 and from 1, you get that as this quantity, when I take the measure of this first set, I'm assuming that the measure is invariant. The measure of this set here will be strict smaller than epsilon by my choice. And the measure of this set right here will be strictly smaller than epsilon as well. So when you, from 2 and 1, this implies that the measure of this difference is less or than 2 epsilon for every so this estimate is important. Okay. I should call this 3. Now we can compare the two things because we have a nice estimate. Okay. So therefore this will be smaller. Yes, B minus plus yes, minus me is 0 plus measure of okay, just the triangle inequality. But this from 3 is smaller than 2 epsilon from our choice. This, by hypothesis, for n large enough, I can take it smaller than epsilon as well for n large enough, for some n0 greater than 1. And this, I'm taking these guys strictly less than epsilon, I can rewrite this last expression here to get something like this. Okay, something that depends on A. Sorry, here this should be B. Plus, maybe it should be a B0 here. I don't know. Okay, but the measure of these sets are smaller than epsilon. And smaller than epsilon. And this is smaller than 1. And then we should get this smaller than 5 epsilon for n large enough. Okay, so there's no square. So this proves that 1 is equivalent to 4. Now we have to prove that 1 is equivalent to 2 or one of these equivalents. But this is, I think I won't do this because of time reasons. But it's actually not that hard to do. It's just here, if this is true, if 2 is true, I need to check that 1 is equivalent to 2. If this is true, if 2 is true, so obviously 1 is this is implying that f me is mixing, because if this holds for arbitrary L2 functions, then it holds for any measurable subset. But you see that mixing implies that correlation functions for L2 converge to 0. This is an argument done by approximating the function by simple functions and using dominated convergence. It's not that hard. Maybe this is an exercise. And then 2, this is an exercise. So this finishes the proof proposition. So I wanted to prove this proposition because now I can prove that if you have a measure preserving dynamical system like a circle rotation or like a shift, you only need to see the algebra that generates the sigma algebra of the measure preserved dynamical system. So now we can see some examples. So my first example will be the circle rotation. The circle rotation, it's interesting because it consists of an example of a ergodic system that's not mixing. So let alpha be a rational number and R alpha be the rotation. Okay. Then the circle rotation is ergodic, but not mixing. And to see the reason for why this is not mixing, you can. It's a lot easier if you draw, but the reason is that if you can take arbitrary intervals, you can take you can choose intervals such that you can choose, for example, an interval I and an interval j, such that if you take the iterates, you using the fact that the circle rotation is an isometry, so that it preserves the length of the intervals. Using this, you can get arbitrary iterates for which these iterates never intersect my interval j. It may happen that for some iterates intersect j, but you can choose a infinity sequence of iterates such that these iterates never intersect the j interval. Okay, so this is basically the argument. Okay. It's with length small such that the Lebesgue measure, which here is implicit that circle rotation preserves the Lebesgue measure. This is 0 for infinity number of n's, but the product of the measures is 0.
Does this work for every interval such that the sum of their Lebesgue measures is strictly smaller than 1? Or
Maybe. I think so. I will check. Actually, you have to choose it smaller than 1/2 for something like that to get this. Yes, there are some relationship between the lengths of the intervals, but maybe it works. Good. And the second interval, the second example I'd like to talk is the Bernoulli shift. just to refresh your memories about what the Bernoulli shift is, I will take a finite set that, for example, we can take the set of numbers from 0 to k minus 1 with k greater than 2. And we consider the space sigma, which is the product of this space over, that is the space of symbols with countable number of entries indexed by integers. And each one of these entries is a number from 0 to k minus 1. So this space, this can be it's better to put this. This is a metric space, compact metric space. With the metric given like this. You take two sequences, and the distance between the sequences is the geometric sum. It's this for every sequence. And there is also a natural operator of the space, which is called the Bernoulli shift, which I'll define now, which is which will take a sequence and take you the sequence 1. This is the Bernoulli shift. With this metric, this is a continuous function on this space. And we can ask about what measures this space support, and this for these measures, which of them are ergodic or which of them are mixing with respect to this map. Indeed, let P0, P1, and P minus 1. These are numbers greater than 0 and smaller than 1, such that their sum is 1. That is, this is a probability vector. Okay. Then we can define a function I will define what I will write here, but we can define a function EL, which is what is this? Everyone saw what is this, right? It's a cylinder. Okay? This is a cylinder. this is not necessarily the same. No, this is maybe R. This is the set of sequences such that X L plus J is X Yj Yj R. The set is called a cylinder. And the set of the cylinders generates the sigma algebra, generates a sigma algebra, such that this function here extends to a measure on this sigma algebra. And maybe you saw this result, but the measure me. Let me put a remark. The measure me, which depends on these probability vectors, is ergodic with respect to the Bernoulli shift. Actually, the fact that it's ergodic, it's actually there's a stronger result related to this. Actually, these measures will be mixing. Okay. Me. It's mixing. And the way to see this, the intuitive reasoning, is that if you imagine that you take two different cylinders. Here I will draw this line to represent the space sigma, and here you have a cylinder. Here you have a cylinder here. And here you have another cylinder. They represent with other color. Okay. I want to prove that to prove that this measure is mixing, it's enough to prove by the proposition that we proved. It's enough to prove that the correlation functions decays to 0 for each one of these cylinders. Okay? But actually so we have to prove this. We have to prove that the measure this measure converges to product of these things as n goes to 0. So what exactly is a cylinder? You forget what you are allowing to be everything what you want in all of those coordinates that are not fixed by the ij's. Okay. And the Bernoulli shift is doing this. This is taking, for example, let's suppose that this is a cylinder A and this is a cylinder B. What the Bernoulli shift is doing is it's taking this cylinder A, and shifting behind. Okay? This portion right here will be my cylinder sigma minus 1 A. And this is what the Bernoulli shift does. Eventually, when you iterate for n large enough, This cylinder here will be iterated, and the portion of the cylinder that's not allowed to move, which is these coordinates, will be disjoint by the coordinates of the cylinder B. So the product of the measure of this, the intersection of these two cylinders, will be just the product of the measure of the cylinder A, because these measures are invariant by the shift, and the measure of the cylinder B. Okay, so this is more or less the idea of the proof of this example. Okay, now to finish the last 20 minutes, I want to talk about the topological notion of mixing. And how these things are related, how the two notions are related. So now we will let F be a continuous map. Okay. Maybe it's better to be a compact metric space. It doesn't need to be a compact metric space, but we'll assume this just to be a little easier. Compact metric space. We say that F is topologically mixing if for every pair of open sets we have that the intersection this is now empty for some n0 for any large enough, and n0 is a natural number that depends on the open set. So some examples. The circle rotation is a system that is that's ergodic but not topologically mixing. Okay. The Bernoulli shift, for the same reason, so for the same reasoning that we did here, will also be topologically mixing. So the exercise that I propose is it's not too hard, but find a mixing system which is not mixing. Okay. I will give more examples. So continuing with the examples. As I mentioned before, the circle rotation and the Bernoulli shift. The circle rotation is not topologically mixing. The Bernoulli shift is. topologically mixing. But there are other examples of topologically mixing systems. If you take, for example, the piecewise uniformly expanding maps of the interval which are the maps such that there is a finite partition of my interval such that in each one of these interval that consists of the partition, the function is the derivative of the function in each one of these points are greater than the exponential of lambda for some constant lambda greater than 0. Okay. And these maps are topologically mixing because by the chain rule, if I take, suppose I pick an interval here, and I want to prove that this interval eventually covers the whole interval. So the length of this interval, let's suppose this interval here is J. The length of this interval J, by the chain rule, if you apply the chain rule here for each one of these iterates, and you use the mean value theorem, you prove that the length of the image of J, as this map is expanding, this will be greater than exponential lambda n for every n greater than 1. Okay. So this proves in particular that the images of this interval J can't be in one interval forever. So they have to escape once, they have to escape once. So we apply the same reasoning for each one of these small pieces. And then you get the images of this interval have to cover the whole manifold. Sorry, the whole interval. I was not trying to not manifold, the whole interval. There is other example that I want to mention. Let me erase this. There's one last example. Which is the Arnold CAV map. And which you take the matrix 2, 1, 1. And you consider the map induced in the torus by the following commutative diagram. I won't prove this now, but Thursday in the teaching assistance class I will prove this. Okay. But I took this example because it's more simple to write. But actually you could take any matrix with with integer coordinates and with determinant equals to 1. And you could ask if the same is true, if the automorphism is also topologically mixing if you descend to the torus. And in the book of Viana there is a nice exposition of this, so I recommend to see more like this. Now I want to finish the lecture explaining one nice application of transfer operators to determine when a dynamical system is mixing. Can I erase this? So now we talk about stochastic stability. Okay, so of transfer operators to mixing. Okay, so what's the setting? We will consider this as any measure preserving dynamical system. And we denote this as the transfer operator acting in L1 functions. So remember that this operator is implicitly defined by the following formula, which is if you take phi and psi L1, then the transfer operator is defined as this, only the unique operator satisfying this property here. This is transfer. This is how the transfer operator is defined. So we'll restrict ourselves to this space. Okay, the space of functions that have mean 0. Sorry. No, okay. Mean 1. And we'll consider the transfer operator acting on this space. So let me write a definition. We say that the system is stochastically stable if there exists a function on this space, d mu, a function which I don't know like this, such that the limit in L1 of the iterates of the transfer operator converges to 0 for phi L1. This is basically saying that my the pair is stochastically stable if there exists a fixed point, a attracting fixed point for the operator. We can give a nice characterization of mixing. Considering stochastically stable, stochastically stability. So the following theorem we are going to prove. Is that stochastically stability implies mixing, but not for this measure mi, for the measure phi star. Sorry, for the measure mi star, where the measure mi star is defined as the measure defined like this. So every measurable subset. Okay? So let's prove this. We want to prove that this holds for the correlation function for sets. We want to prove that correlation function for sets converges like this for every A, B. Here. This is my M. Okay? So that means. So what we're going to do, we'll define a new function. Which is a function, you take the characteristic function. Okay, we define this function here. Now, remark, as this function phi star is in my space d mu, so the function g is also in the space d mu. Okay, it will still be positive by definition, and if you take the average will be the average is average here, but this is 0 because the function phi star is in d mu. So this function here. Yes. No, it's just we only have to rewrite this in terms of the transfer operator. How is this will be written? Yes. Now. This, by definition, the measure of this set is equal to the measure, the integral of phi star dmi. But now I use the definition of the transfer operator. This will be the integral in f z. Okay. Now this right here, I can rewrite it like this. Yes. And here appears the phi composite of Fn, the mi. Sorry. Okay. Now I apply the definition of the transfer operator. In B, yes. And okay. Okay, I can move this. I can take this and put here by linearity, but this, what's inside of the domain of the transfer operator, this is exactly the G. Okay? This is exactly G. And the chi-A, I can just take this, I can write it like this. Okay, I just remove the chi-A, put it here. And what we get exactly the integral, and let's say, yes, the integral of the n iterate of the transfer operator applied to G in A. But as we are assuming stochastic stability, this converges to phi dmi and A. Okay, this is by stochastic stability. But what is this? This is exactly the measure mi star of A. So we got what we aim to prove here. And this finishes the proof. One nice application of this theorem is that we are able to prove, that uniformly expanding maps of the interval are mixing using this theorem. Piecewise expanding maps because we can prove that indeed the uniformly piecewise expanding maps of the interval are stochastically stable. Okay. And then a corollary of this theorem is that they are all mixing. Okay, so this finishes the lecture for today. Wednesday we continue to talk about mixing, but we'll study other ways to talk about mixing. We'll talk about weak mixing systems, and that's it. Anyone has any questions?
Why can you guarantee that LF is in L1 and not L2?
LF. L.
Yes.
The L1 here. It's because you have this inequality. Take. So it's in L1. Okay. This is because this is by definition of the measure preserving dynamical of the transfer operator. Okay. But you can talk about one if you want. Was that the question? Sorry.
Yes.
Oh, okay. So we'll finish here.